this is the July 17th weekend lecture for Algebra 2. All right, so what we're going to cover in this lecture here is we're going to finish up Unit 3, and we're going to start a little bit of Unit 4. All right, so we're only covering 4 lessons, right? So similar to last weekend, we're only covering 4 lessons. However, we're going to have a unit test in between them, okay? So let's look at again what the overview of this looks like. So if we scroll to where we ended with Unit 3 here. So we're going to cover today lesson 3.10, 311, and then obviously 312 is the wrap up and test for this unit here. Okay, so we only have 2 new lessons with new material and then our unit test. All right, and obviously I would suggest that when you're going through this would be a really good place to break naturally, right? If you wanted to pause the lecture or stop the lecture for the day, finish up Unit 3, and then come back obviously at your own leisure here. Because what we're going to also cover is Unit 4, at least the first couple here. So we're going to look at obviously our overview for Unit 4. We are then going to look at Unit 4.1 and also 4.2 here. So we're going to really try to just get started so that we can rock and roll into Unit 4, the new material, when we come back on Monday. All right. So again, I think a natural breaking point would be obviously at the end of Unit 3 here, and really trying to make sure that you stay at this pace here. Okay, obviously if this is a little bit too much, remember you do have that 4th solo week, but the schedule I have us on here has us finishing all the material in our 3-week period, leaving you that 1 week to finish up your final exam here. All right, so let's get on into it then. All right, so if we look at lesson 310 here, okay, we've been dealing a lot, obviously, over the last couple of days here with logarithms. All right, so what we're going to do is we're going to look at some of the applications or the real world applications, right, of logarithmic functions. So if we get into it here, the first application we're going to take a look at is what happens if we pour a cup of coffee and leave it on the kitchen table, right? Hopefully this is the same question you have that I do, is how long do I have to wait before I can start drinking this coffee without burning my mouth here? All right, so if we think about some of the things that'll happen to this cup of coffee, all right, there's a couple statements here of what they think might happen. And basically all of them are trying to address how a cup of coffee cools. All right, so we can look here. Does it drop slowly and then steadily to room temperature? Does it drop quickly to below room temperature and then bounce back? Or does it drop quickly but then levels off as it gets closer to room temperature? Okay, so those are kind of our 3 options here. And hopefully, we would all be able to get that it's going to drop. Oh, I don't know why it's not letting me answer this here. That it's going to drop rather quickly, but then level off when it gets towards room temperature. Okay, it's going to level off towards room temperature, because think about it here, right? Your liquid in the cup is always going to try to get to the temperature that is, or the room, right? The temperature that is the room. So if it's really hot in your room, right, your drinks will stay a little bit warmer. If it's really cool in the room, right, it'll get a little bit cooler. All right, so that's how this cup of coffee cools here. All right, and hopefully we can remember here, right, this is an example of an exponential decay. So if it cools down really quickly, then starts to level off, hopefully you're going to notice that this looks like an exponential decay function here. All right, so if we look at this cooling coffee animation or video here, it'll explain a little bit more in detail.
Take a look at a graph that describes what happens to the temperature of the coffee. Let the vertical axis represent temperature and the horizontal axis represent time. Start by marking the temperature of the coffee when it is first poured. Since the coffee will not get cooler than room temperature, draw a dotted line to indicate where the temperature will level off. Finally, here is the curve that shows the temperature dropping and leveling off as it approaches room temperature.
Okay, so again, if we look at this, initial temperature of our coffee might be kind of high, and if our room temperature is this dashed line here, right, we're not going to go below the room temperature. We would need something like ice, obviously, to make it go below that room temperature here. And if we look at this function, all right, again, it looks like our exponential decay functions that we've been dealing a lot with. Right? And it looks like, again, it's leveling out at this room temperature, where room temperature seems to be a horizontal asymptote, right? A horizontal asymptote there, okay? And what we can do here is we can find, or we found for you, right, an equation that you can use. And the one that we're going to use here is called Newton's law of cooling. All right, it's Newton's law of cooling. And again, don't let this equation bother you, right? It's just standing for something where we give you the variables, right? So if you look at this here, we've got TA plus T0 minus TA multiplied by e to the power of KT. All right, where TA is our ambient temperature or our room temperature, right? T0 is the initial temperature, T lowercase t is time, and K is a constant. All right. And obviously then it's good to notice that it's negative KT, all right? And this is a great reminder that this represents our exponential decay, right? It's going to represent our exponential decay. All right, so if we look at how Newton's formula works here, we can take a minute and watch this animation.
Sir Isaac Newton developed a mathematical model called Newton's law of cooling that may be used to calculate how long it will take the coffee to get to a drinkable temperature. What do all those letters stand for? It looks complicated, but it really is not. Here's what they all mean. T of T is the temperature in degrees Fahrenheit of an object at a given time T. T sub A is the temperature of the surrounding or ambient environment. T sub 0 is the initial temperature of the object. K is a positive constant. How do you use Newton's law of cooling? Let's look at a specific example. Suppose you pour a cup of coffee that is 200 degrees Fahrenheit and leave it on the table in a room that is 68 degrees Fahrenheit. 10 minutes later, the coffee is 150 degrees. How long before the coffee will be 100 degrees Fahrenheit? Start with Newton's law of cooling and then write down the values you have been given. You want to know what value of T will make T, T.
Okay, so really complicated when he starts talking about all those T's here. So let me pause for a second. All right, first thing I want you to notice here is that both of these temperatures are in the same unit, right? Degrees Fahrenheit. Degrees Fahrenheit. That is super, super important, okay? You got to make sure you're in the same units, all right? Next thing you're going to notice here is that you need to write down what you have. Write down what you have. So if we look here, T0, remember that's our initial temperature. That was 200 degrees Fahrenheit. Our room temperature we know is 68. All right. And the only other piece of information that we've been given at this time was that after 10 minutes, right? So little lowercase t, our time was 10 minutes. We had a temperature of 150 degrees. Okay. So if we look here, right, if we use what we have, the only variable that we are currently missing here is our K constant, right? Because remember, E is not a variable here. E stands for an actual value, right? That's our a value of about like 2.14, I believe, right? It's on your calculator, okay? So we need to then solve for our K constant in order to answer the question that he just asked, how long is it going to take us to get to 100 degrees, right? Well, we're still missing right now a very valuable constant that we need to solve that question. So we've got to use what we have so we can solve for our K constant here.
Equal 100. In order to answer this question, you first have to find the value of K. In order to calculate K, fill in all the other known values. Simplify, then solve for K by using the natural log function.
Okay, again, a reminder, because natural log, ln is log of E, right? And log of E, or log base E, undoes our e to the power of our exponent function, right? It undoes that function there for us. All right.
Now that you know K, put that into Newton's law of cooling. Then, since you want to know what it is when T is 100, substitute 100 for T and solve for T. Approximately 30 minutes after the coffee is poured, it will be 100 degrees Fahrenheit.
Okay, so again, that would be how we work this problem here. All right. And they did skip one baby step there, right? They already did for this 132 here. They already did the 200 minus 68, right? Because our starting temperature was 200, our room temperature was 68. So that's how they got that 132, in case you're wondering. All right. But again, hopefully not too terribly difficult. You can do this for a lot of different problems here. Okay. You can do this for a lot of different problems. So it's all about, again, finding the right equation, figuring out what each of the variables stand for, writing down what you have, and then really analyzing the situation to figure out what you're really looking for. Okay, so again, if we look at another example using Newton's law of cooling here, we can look at cooling a soda can. All right, we can look at cooling a soda can. All right, so right now, if we look, we have room temperature soda. Yuck. All right, we want to cool it down so that it is a nice drinkable temperature, and we want to cool it down so that when you pour it over ice, the warm soda doesn't melt the ice quickly. All right, so right now, our initial temperature here is 74 degrees Fahrenheit. All right, after 10 minutes in our fridge, which is at 38 degrees Fahrenheit, the soda is 70 degrees. So how long is it going to take us to cool this soda to 60 degrees Fahrenheit? All right, well, the first thing we need to do is find our equation that we're going to use. Right, so obviously we're going to use Newton's law of cooling for this one. Then what we're going to do is write down all the variables that we know from this problem here, right? So our initial temperature here, our T0 was 74, all right? We know that our room temperature for our fridge is 38, right? So that's TA, that's 38, all right? And we figured out that when T was equal to 10, right, 10 minutes, our output value, right, the temperature of our soda was 70 degrees, okay? So we have a lot of good variables here, and that's obviously step one, okay? Step two is we have to substitute in to our equation here and then simplify in order to solve for our missing constant here, and our missing constant is this K value. All right, and hopefully you realize the first step is obviously just substituting in the values, okay? Then we do 74 minus 38, and that's how we get our 36, and we move this 38 to the other side by subtracting 38 from both, so we're left with 32 equals 36, e to the power of negative 10k. All right, then we divide both sides by 36, which is how we get this value right here. All right, and then we're left with this value constant is equal to e to the power of negative 10k, right? Since we have to solve for the exponent, we need to undo this function, all right? And since we have it to the power of, with a base of e here, we need to use our log function with a base of e, right? So our natural log, ln function, okay? So when we apply ln to both sides, what actually happens here is ln and e cancel, right? Remember, ln and e cancel. So we're left with just our exponent, which is negative 10k, and that's going to be equal to ln of the left-hand side of our equation here. All right, so then we obviously get an output value, right? Because we can plug that into our calculator, ln of 0.889. That'll give us approximately this value here. All right, then we divide both sides by negative 10, and we have our K output value, right? We have our value of K here, okay? And now that we have our value for K, right, we can go back to our original equation. Oh, sorry, that's going to be the next step here. But But now that we have our constant k, in order to solve this problem, we can now go back to the original information we know, and now plug in our constant k in order to solve for the question that we want to answer, which is how long will it take the soda to cool to 60 degrees Fahrenheit. All right, so all right, now we've got it. Beautiful. We restate what we know. And now we have that k constant. So very simply here, we substitute and simplify. All right, we substitute and simplify. All right, and again, finding a very similar process, we get ourselves down to a constant is equal to e to the power of our value we need to solve for, right? And again, in this case, it's going to be this t here. All right, so again, we undo this e to the power of function, right, or by using our log base e, or our natural log function. All right, and once we've done that, we can then solve for our value of t. All right, and then as always, it's always nice to restate the solution. So when we get our value of 41.8, that's going to be in minutes, right? So it's going to take us 41.8 minutes for our soda to cool to 60 degrees in a 38 degree Fahrenheit refrigerator. All right, so that's how long it's going to take. Okay. Logarithms can also be used in archaeology, right? And I know I definitely mentioned this in my bio class, and I know chemistry talked about it a little bit. But there's this thing called carbon dating, right? So we can figure out the relative age of ancient things by measuring how quickly something breaks down. All right, using this thing called half-life. All right, so it's a really cool thing, and again, that's not the point of this, right? But we're able to use a chemical property, right? We're able to use a chemical property that is found in biological creatures, right, or biological components, right, in order to date something back. Thanks to this mathematical relationship here, we're able to again use it to date fossils. All right, so what this is it's C of T is equal to CO 2 to the power of negative T over 5730. All right, and C0 is the amount of carbon originally in the fossil. T is obviously the time that passes, and C of T is obviously the amount of carbon that is left here. All right, so let's take a look at what, a little bit more in depth here about what this carbon-14 or radioactive dating is.
Archaeologists use mathematics for another kind of detective work, determining the age of an artifact. Carbon-14 is a radioactive substance found in living organisms that decay after the organism dies. The half-life of carbon-14 is 5,730 years, so you can write an equation that represents the amount of carbon-14 present T years after the organism dies. Suppose an artifact contained 63% of the amount of carbon-14 it contained originally. How old is the artifact? If you divide both...
All right, and pause before he goes and solves that. Hopefully you noticed what they did there. It said 63% of the original amount of carbon it was supposed to have, right? So we changed CT to 0.63 of CO, right? Again, this 0.63 being 63%. And again, changing from C to CO because it's saying 63% of the original. So 63% times by the original is how much we had left. All right, so if that's what our equation looked like, we could then solve, and he's going to explain that here in the video.
Sides of the equation by C sub 0, you are left with this equation. Now solve for T. We conclude that the artifact is approximately 3,819 years old.
All right, and take a look here at the steps. All right, take a look here at the steps. So we'll break them down, I believe, on the next slide here. But again, we got it to where we have a constant on the left and our exponent on the right here, right? And again, to undo, right, to undo something without a base 10 or a base e, right, we have to multiply both sides by either our natural log or our log base 10, right? For this one, they chose the natural log here. But as long as you're consistent, that's what matters here. All right. So now if we have log of 0.63 and log of, natural log of 0.63 equals natural log of 2 raised to the power of t over 5730. All right. Again, what happens here is if we have our log function raised to the power of something, right? We carry this out in front, right? So this exponent now becomes a constant out in front. All right, so we have our negative t divided by 5730. All right, and we're able to rearrange our equation to isolate this value for t. So we divide both sides by ln of 2, which is how we get ln of 2 in the denominator. And then obviously this is a t over negative 5730. So we're going to multiply both sides by 5730. Negative 5730. So what you're going to notice here is there's a negative sign, and then we would plug this directly into our calculator, and we're able to calculate out about how old this fossil is, right, about how old this fossil is. All right. We can also look at logarithmic functions as growth functions, right, not only decay functions, okay? And we saw earlier examples, again, of course, of compound interest. However, there are some that will not allow for this infinite growth, okay? Will not allow for infinite growth. So it could start out growing really, really quickly, and then, of course, it can approach a horizontal asymptote, all right? It can approach a horizontal asymptote. And something that this is similar to is our carrying capacity, right? Or we talked about it in bio class, again, about how many animals can be sustained in an environment based on the amount of energy available, right? That carrying capacity. So we can look at things, again, in terms of logistic growth, right? In terms of logistic growth. So what does that look like? What does that mean?
Newton's law of cooling and carbon-14 dating are examples of exponential decay. Exponential functions are also used to model growth for such things as savings accounts and population. When an exponential function is used to describe population growth, the underlying assumption is that the population will continue to grow without bound. But what about situations where some other factor, such as limited food and water, keeps the population from growing without bound? These situations are best described by a logistic growth curve. The graph of a logistic growth curve looks like this. You can see that in this section, the graph looks like an exponential growth curve. But in this part, the graph changes. The rate of growth slows, the graph levels out, and approaches the horizontal asymptote, y equals L. The function that produces a logistic growth curve looks like this. As you can see, L indicates the upper limit for the population. L is sometimes referred to as the carrying capacity. How do you think the value of B will affect this function? You can compare the two functions shown here by graphing them. Notice that the only difference between ft and gt is the value of B. The larger B is, the faster the function reaches its carrying capacity.
Right? So in terms of looking at this, right, to give you an example of blue versus red here, okay, this would be like saying for every one bunny, it's going to multiply and give 2 new organisms versus if you're going to give 8 new organisms per every bunny. Obviously, those the rate where you have 8 new organisms per every one is going to reach that carrying capacity much, much quicker. All right, and again, it doesn't always have to have this upper limit here, but when we're talking about this example here, obviously there's not an unlimited supply of food and water naturally available in the environment for our bunnies here, right? So they've got to hover around a certain limit of animals that can exist in a certain area, right? So looking at this example here of our rabbits, all right. Looking at this example here of our rabbits. So our carrying capacity, right? Our carrying capacity. Oh, I was hoping it would just give us the answer there. All right, so our carrying capacity is this value here of 1,000, right? So again, if we go back to the
Newton's
equation
law of cooling.
here.
Notice that the only difference between Ft and G.
All right, so if we go back to this equation here, and on your study sheet you'll have this. All right, so we have L over 1 plus CT minus BT, right? And again, L was our carrying capacity. So right there, our carrying capacity was 1,000. All right.
Here is an example problem involving a logistic growth curve. Suppose this function describes the growth of a population of rabbits on a particular island, where T represents the time in years since the rabbits were first introduced on the island. According to this model, what is carrying capacity on the island as far as rabbits are concerned?
Okay, so again, the highlight there is T being time since the bunnies were first introduced on the island. All right, so we already figured out that obviously our carrying capacity is 1,000 bunnies. That's what we
This
can
question is really asking, what is the value of P of 0? You substitute 0 for T to get the answer.
Since P of 0 equals 100, you conclude that initially there were 100 rabbits introduced on the island.
All right, and again, that one was pretty obvious here since it was time introduced. Time introduced, obviously that time was at time 0 when they first came to the island. All right, and we can plug in a 0 for our T, and where P of T, we're then able to solve for by plugging in and using our algebraic operations. So we were left with 100. Right, we're left with 100.
To answer this question, set P of T equal to 500.
Okay, so when will the population reach 500, right? That's saying, again, P of T is equal to 500. And now we have to solve for our T exponent. We have to solve for our T exponent.
And use logarithms to solve for T. The solution tells you that after approximately 11 years, the rabbit population will reach 1/2 of the island's carrying capacity.
All right, so again, the key here is getting us down to our exponent on one side isolated and our constant on the other. And luckily for us with this one here, again, it is our ln our base is e, so we can use our ln function here to undo this e exponent. All right, so when we multiply both sides here by our ln function, ln and e cancel out, and we're just left with this constant here. All right, and then we have ln of 1 over 9. All right, so we're able to easily solve there for how long it would take for the population to reach 500. All right. So then if we look at another example here, just like Newton's law of cooling, all right, there is a constant here that quickly can show how quickly or how slowly the growth happens here. All right, so looking at, again, continuing to identify our variables here. All right, so again, a rabbit population has a carrying capacity of 1,000, and we're saying now that the growth rate is 0.2. All right, we're saying the growth rate is 0.2. After 1 year, the population has grown to 120 rabbits. All right, assuming this is our variables here, the first question is, what is the value of the constant C? All right, if L is the carrying capacity, B is the growth rate, and T is the time elapsed. All right, if T is the time elapsed. All right, so first here we need to identify what the values of P of T, L, B, and T are. All right, so we obviously said that we want to look at the population has grown to 120 rabbits, right? So our P of T is going to be equal to 120. All right, our carrying capacity is still 1,000. Our growth rate here, though, our constant B, we said is 0.2. All right, so that's where this one's going to differ here. And then to confirm, it's after 1 year, so T equals 1. All right, so that's how we would look at this problem here. All right, then if we go here, what's the approximate value of C? What's our approximate value for C? So for this one, obviously I'm not going to do the work for you, and you should double check it to make sure that I'm right, but we would just plug in all of our values into this equation, and then we would use our various operations here to solve for C, right? To solve for C being our initial number of bunnies, right? And when we did that, right, we're going to find out that the C value equals 9 there. All right, and again, how this works is we plug in our values that we know, right? We multiply our denominator by both sides, right? And we move 120 to the other side. Okay, we subtract our 1 once we've simplified. All right, and then we have CE to the power of 0.2. Okay, and what we can do there is we can use our ln function, right? We can use our ln function, and we can use our one of the properties here. Okay, we can use our property of ln, and if we have the ln of two things multiplied together, it's like having them being added, right? It's like having them being added. All right, and then what we can do is we can then solve for our function here. All right, we can solve for our function. So C is equal to e to the power of 2.192. Or again, if we were to solve that out, it would be a value of 9 there. Okay. So I'll let you look at those on your own, but again, understanding that we will give you equations, all right? You just have to understand how to approach the problem here, all right? And again, these are really good problems for you to try, but really the key comes down to identify the problem, okay? Figure out what information you're given from your scenario, all right? Then the next step is figure out what you're looking for, all right? What are we looking for? Then ask yourself, am I missing any critical information in order to solve the problem, right? Like for this problem, we were missing originally our K constant, right? So we had to do that first before we could then find the question we were trying to solve, right? And then regardless, the next step here is plug in what you have, solve for what you're missing, right? Using correct operations and making sure your calculator skills are on point. All right, so then again, I'm going to let you try these because they're a little bit longer than I'd like to spend with you on this video. And again, you can practice these guys on your own. All right, but again, you're given the equation, so the equation shouldn't be the hiccup here. All right, you should be able to input, again, what you have, look what you're, figure out what you're looking for, and then solve. All right. So then if we want to continue this moving forward here, we've talked a little bit about it in various lessons here, but now looking at compound interest, all right, with compound interest. All right, so again, I love this one because it always puts it in terms of money, and obviously, you know, we'd all like to have more money at some point. I think, at least I'd like to think so, right? So if we can use something like compound interest, again, I always like to say make your money work for you, right? Make your money work for you. So how does that work here?
We've seen that exponential functions show up in many real-world situations. In this study, we look at what is perhaps the most practical application of all, personal finance. For example, you may want to answer the questions such as, how much can I afford to pay for a car? How long will it take for me to save the money? And if I borrow money instead, how long will it take for me to pay off my debt? Let's start with savings. Suppose you deposit $1,000 into a savings account that pays 5% interest, compounded annually. After 1 year, the amount in your account is $1,000 plus 5% of $1,000. This is the same as 1,001 plus 0.05. After the bank adds interest the second year, you have the amount from year 1 plus 5% of that amount. So again, you multiply by 1 plus 0.05. You can see that each year, the amount in your account is multiplied by 1 plus 0.05. This leads to a function that expresses the amount, A, that will be in your account after T years. The previous example assumed that interest was compounded once per year. But what happens if interest is compounded more frequently? For example, here is a bank that advertises savings accounts with 5% interest compounded monthly. When interest is compounded n times per year, then the interest rate applied each compounding period is a fraction of the annual rate. This is written as R divided by N. The account grows more quickly because interest is being applied more often. A general formula for calculating the amount of money in your savings account is shown here. In this formula, A is the amount of money in your account. P is the principal, or the amount of money you deposit originally. R is the interest rate per year. N is the number of compounding periods per year. T is the number of years. Does the number of compounding periods really make a difference? Let's do some calculations and see. In this example, more frequent compounding makes about a $2,600 difference.
Okay, so that could be a really big difference here. All right, so again, this is always a really good real world example here. All right, and obviously it works the opposite direction when you're not dealing with, a savings account or putting money in the bank, right? It also works with paying off loans and debts and all of that stuff, right? So of course, making a wise investment here is going to be a good idea. And for the sake of time here and to give you more practice, I'm going to let you try these on your own, okay? And we'll highlight this here. All right, there is a difference between compounding at certain intervals, right? Like monthly or yearly, like that last one is, and compounding things continuously. That's every second of every day. So let's take a look.
Sometimes banks advertise that interest will be compounded continuously. This means that at any moment in time, interest is being added at a rate proportional to the balance at that moment. Used to calculate the balance in an account with this form of interest uses an exponential function. In this case, the base of the exponential function is an old friend, E. In this formula, P is the principal, R is the interest rate, T is years. If you invest $2,000 in an account that earns 6% interest compounded continuously, how long will it take the account balance to grow to $3,000? To answer this question, substitute known values in the formula and then use the natural logarithm function to solve for t. We find that it will take nearly 7 years for your account to grow to $3,000. What about taking out a loan? If you borrow money to buy a car, how much more do you end up paying than you would if you paid in cash? There are more variables to be concerned about in this situation. Think about all of the questions you might have to ask if you buy a car. When you put money in the bank, you're loaning that money to the bank. They pay you interest for the right to use your money. But when you want to use the bank's money, they charge you interest and it's higher than they pay for your savings. This is one way banks make money.
Most people are shocked to learn how much money they have to pay in order to pay off a loan. We'll just focus on how the interest on a loan grows. Suppose you decide to purchase a new car. You find a car with a selling price of $15,000. You pay $5,000 in cash and obtain a loan for the rest. Your interest rate is 10% annually.
After 5 years, if you make no payments, what will your loan balance be?
It depends on how often your bank compounds interest. At a bank that compounds once per year, your loan amount will have grown to $16,105.10. If it compounds monthly, your loan balance will be $16,453.09. But if your loan interest compounds continuously, the balance will be $16,487.21. Because the actual interest you pay is more than the percentage officially posted, you will often see the letters APR or annual percentage rate attached to a loan like this. The same goes for savings also. In that case, you will see the letters APY, which stand for annual percentage yield. That means you will actually earn more interest than the posted rate due to the compounding of interest.
All right. So then obviously here, hopefully you picked up a trick or two. If you are getting a loan, right? If you're getting a loan, or you're using a credit card or something like that, right? If you're getting a loan or need to pay back money, you want a really, really low interest rate, right? As low as you can possibly get. But if you're having something like a savings account or a banking account, you want a high interest rate where they're going to give you more interest on your money, right? They're going to give you more interest on your money. All right. So if we take a quick look here at our study guide, all right, this one is going to be mostly beneficial for you for realizing, having a place to compound all of these new equations that we learned. All right, all of these new equations. And obviously, yes, it's good to have a practice example of these as well. All right, but we really talked about 3 of those equations, and I guess 4 if you want to count the interest rate equations that we looked at in the last sheet here. All right, but you can quickly go over that and fill that out as you're going through. To look at the checkup here, it's going to be obviously more practice problems, okay? So all of them are going to be word problems here, okay? So we're giving you the equation and we're asking you for specific things. So again, the key there is going to be, what do you have? What do you need? What are we looking for? All right, that's going to be the key here. What do we have? What do you need? What are you looking for? All right, all equations are given there. All right. And then the final step here is being able to look at it graphically. Okay, being able to look at it graphically. And a lot of the times we're going to be dealing with, like we said, this kind of capping out or this carrying capacity here when it's getting reached. All right. So after you do a couple of those practice problems or the whole thing, right? That's always my hope, is you do the whole thing, but at least do a couple of them. All right. You have this quiz for 3.10. All right. So that's 3.10 right there. Now, if we get into 3.11 here, we're going to look at comparing and analyzing different function types. Getting into it here, we got to start off with just a reminder of what is a function and what is not a function. All right. And it's easy when we were dealing with it graphically, right? Because that's obviously, if it passes the vertical line test, it is a function. But in general, remember, a function is where there is only one y value to one x value. Okay, there's one y value to every x value. So if we look here, things that are functions, right, that would be our linear function here. All right, this guy is not a function because we're going to have multiple output values for our y's and our x's, so that's not a function. All right. Now looking at these two guys, so y equals x squared and x equals y squared. All right. So y equals x squared is a function, but its opposite here is not. All right. Its opposite here is not, because again, the key is that we can only have one x value for every y value, right? Or every x value has its own y value. All right. And so we have to have a unique value for every x input. All right. So then moving forward here, remember, like I just said, we have the vertical line test here. All right, we have the vertical line test. So if we look at this function, it passes the vertical line test, so it is a function, right? This one fails because it does not pass a vertical line test. Obviously, this guy does not pass the vertical line test, right? And this was our more complex looking equation that we had. And then finally, this last one here was our linear line, and obviously that passed the vertical line test. All right. And notice here, I just want to highlight the difference. This is our y equals x squared, and this is our x equals y squared. All right. And again, every x value has to have a y value, right? And it can only have one y value. So the reason this fails here is because if I look at 2, right, it looks like it's at about maybe 1, maybe a little over 1. But regardless, when I'm at x equals 2, I have a negative 1 and a positive 1. Or sorry, a positive 1 and a negative 1, right? And that fails as a function by definition, right? And how the easy way we can look at that is, again, this vertical line test. All right. And then we dealt a lot with, especially in semester 1, with these parent functions. So reminding us what these look like here. Linear, it's going to be our straight line, right? That's where we're going to have our y equals mx plus b here, right? Our y equals mx plus b. All right. And the parent function, okay, the parent function for a linear line here is where we have f of x is equal to just x. All right, if we have it equal to x squared, that's where we get this quadratic function, right, with this parabola shape. If we have the absolute value of x, that takes it from being this straight vertical line here to looking like a V, where it has a sharp turn at this point, 0, 0. All right. Then if we go beyond that, right, we can look at our other functions. We had our cubic, our quartic, and our quintic, or our x to the 3rd power, x to the 4th power, and obviously our base x to the 5th power. Okay, and something I want to point out here is that obviously we know that there are more turns here between a cubic and a quintic. I know they look very similar, and we talked a lot in semester 1 about the differences between that, right? It's just do know that yes, these two, even though this is to the power of 2 and to the power of 4, they look kind of similar. There's obviously some differences, and they get more exacerbated as we look at these lines here. Okay, so I will let you guys go through these here and really have them matching up. But oh, I guess we have time. We can go through it here. All right, so if we look at linear and absolute parent functions, they don't have any curves, right? Those were our straight lines, and it's either straight line or right the two straight lines that form that V shape. All right, exponential and our logarithmic, okay, they obviously have some curves, and another thing is that they have asymptotes, right? Either vertical or horizontal or both, right? They have those asymptotes there. All right. Then we're looking at our odd degree polynomial versus our even degree. All right, and even being like 2, 4, 6, 8, and our odd being obviously 1, 3, 5, 7. All right, and so if we're looking at our odd degree polynomials, all right, they have one end goes down and one end goes up, right? Think about our linear line, right? One end, the left side is down and the right side is up. Same behavior for our cubic and our quintic. All right, with our even degree polynomials, that's where both end behaviors go up, right? We're making those U shape, right? The up cups. Okay, and then I don't want to spend a ton of time going over this here. All right, but we have transformations for functions, right? So what does it look like in terms of the actual equation? What does it look like in terms of table values, and what does it look like in terms of graphs, right? But in general here, if we're reflecting across this y equals x, we flip our x and our y, and obviously the graph is reflected across that imaginary linear line. Okay, and then if we have this reflection across the x-axis, right, that's where we flip across the x-axis and make it look like a mirror. All right, and we multiply our entire function by that negative value, right? We have negative f of x. All right, when we reflect across the y-axis, again, we're flipping across the y, but now we are plugging in a negative x value into our function. Right? We're plugging a negative x value into our function. All right, then if we're doing horizontal shifts or slides, right, that's where we're actually looking inside at our x value, and we are adding or subtracting a value k, moving it either left or right. All right, then when we have a vertical shift, again, that's up and down, and we're adding a value to the entire exponent, right? So it's, or sorry, to the entire function, so it is outside of the entire function. All right, then if we're going to stretch or compress, we're going to multiply by a constant for our entire function, right? And if the constant is greater than 1, it's going to be a stretch, pulling it away from the x-axis. And if it is a compression, it's going to be obviously pulled closer to the x-axis. All right, and then we noticed here, all right, horizontal shifts and vertical shifts. Okay, and noticing the difference here. Okay, noticing the difference. All right, so then we talked a lot about reflections, right? It could be reflections across a lot of things. Our vertical reflection, a horizontal reflection, right? Reflecting across that line y equals x, maybe reflecting across a asymptote, right? A lot of different things. But this one here, okay, this one here is going to be our reflection across the line y equals x. All right, a reflection across the line y equals x. And again, the easiest way for me to notice it is if I look at this graphically here. All right, it is reflected across this imaginary linear line. All right, and then of course, if you like the tables and what that does to the equation, okay, so the table of values are right here, so you could look at those and notice, of course, that we flipped our x and our y values, okay, or you could notice that the equations had shifted where we replaced x with y and y with x, okay. Then we talked about translations here, okay, translations. So if we look at this here, all right, the parent functions are the same, and again, it looks like it was translated up, right? So this equation here would be 2x plus something, right? And to for me, it's a little bit more difficult to see how far we've moved up here, but it's very obvious when you look at the values here, right? So for 0, 0, or I'm sorry, for the 0x, we have 0 here, right? This output value is 1, while this output value is 5. So it looks like we've added 4, but of course, we always got to check another point to make sure. So if I go to 2 here, right, it goes from 2 to 4. So this is going to be 2x plus 4 on the outside of the exponent because it's a vertical shifting up. All right, then if we look at this next guy here, all right, we've even gotten the equation. So this function here is a vertical stretch, right? And I know this by a lot of different ways. First, graphically, it's pulled away from the x-axis, so that's going to be a stretch in the vertical direction. We can also notice here on our equation that we multiplied our x component by a value greater than 1, so it is a stretch. And then if we notice here, of course, for our values of x, they are the same, but the values of y have changed. They have increased by a factor of 5 for every value, again indicating you are stretching or changing along the vertical axes, right, since we're dealing with our y. Okay, then I really want you guys to do these on your own here because obviously there is a lot of different things that can get broken down here. But in general, this parent function, okay, this parent function is going to get stripped away of this vertical stretch, right? And then it's going to get stripped of this translation here. So our base function for this guy is actually 3 to the power of x. All right. And then you can continue to identify, okay, so then what does that look like? What does the property of my graph look like? What do all of these different components end up doing to my graph? All right, and when you are able to look at that, right, we're able to identify all of these different things. So if you look here, all right, so again, the parent function here is 3 to the power of x. Our domain for an exponential graph like this is all real numbers, and our range is any number that is above 0, right? Any positive real number. Okay, and because of this, we know the x-axis is an asymptote, and we have our y-intercept. Okay, if it was just this base function of 3 to the x, our y-intercept would be at 0, 1. But obviously, obviously here, since we have this value of 4 out front, the intercept is now at 0, A times B, or 4 times 3, which gives us 12 here, which gives us 12. All right. We have this point 136 being on the graph. Oh, and something I didn't mention here, all right, is again this plus 1 to our x component here, all right? So our parent function was translated to the left. And since we have no plus or minus on the outside here, we have no translation horizontally. All right. And I think I mentioned it, maybe I missed it, but again, this 4 value out here indicates that it was vertically stretched. All right, and then you can take a look here at what each of those individual modifications does to the parent function and what it looks like when it's added together there. Okay, so now we can go a little bit further into this and we can distinguish between different kinds of functions. All right, so if we look here, below is a graph of one function and the equation of a different function. Okay. So we got to see if we can answer the question here. We've got this as a graph, and we've got this one as an equation. All right, so do both of these functions cross the x-axis? All right, do both of these cross the x-axis? And if we look at our answer here, only the graph function crosses the x-axis. All right, only this function crosses. And we can look here because remember, that was one of our characteristics for the parent function of 2x, or sorry, b to the power of x, right? B to the power of x. So that says that it doesn't ever cross the x-axis because an exponential function has a horizontal asymptote at our y equals 0, right? So only the graph function crosses the x-axis. All right. Okay. So again, like I said, we can recognize that this is our exponential function, again, meaning that horizontal asymptote at the x-axis here. All right. Now, something that we want to point here is that if this had been a transform graph, all right, normally we'd have our horizontal asymptote at the x-axis, all right, but if we had this -1, then we would have shifted the entire graph down by 1 value, right? So we then would have had it cross the x-axis at 0, 0, right? We would have had it cross the x-axis at 0, 0 because we would have shifted our asymptote. Okay, so then here, if we look at these two functions here, right, the question is which of them has the largest y value? Which of them has the largest y value? Okay, and if we look here, we would be able to see, we'd be able to see without looking at the function, we'd be able to pick out some identifying features here. All right, and the biggest one that I notice here is that this has a negative sign, right? This has a negative sign. So out in front there, right, with our exponent, or sorry, with our variable, right, that's indicating that we're going to reflect across the x-axis, right? We're going to reflect across the x-axis, which means that we're going to have a lot of negative values, right? Our graph is going to be decreasing, right? It's going to be decreasing both on our left and our right side. All right, so that's going to tell me here that that's going to be a very negative sloping or negative pointing graph. Whereas this one is our absolute value parent function, right? And since this constant out in front is positive, we are going to have both sides of our graph again increasing due to this absolute function graph here. All right, and you can look at all of these different points here on your own and spend some time, but essentially, right, you should be able to look at these images or look at those equations and kind of paint an image in your mind of these two graphs. And that's exactly what I viewed in my head. Minus, obviously, I didn't really focus much on the translations left and right because all we were talking about was in this y direction, right? So for me, when I was looking at it, I spent majority of my time focusing on anything that would have an impact in the y direction. Okay, so being able to compare graphs is going to be obviously really, really, really beneficial here. All right, and then if we look at these three graphs here, okay, it's asking you to describe how they're similar and how they're different. Well, obviously they're all base 2, they're raised to the power of x. All right, but this is the parent function. This one is reflected across the y-axis. This one is reflected across the x-axis. So the behaviors of starting and ending are going to be different here, where this one and this is the only one that's increasing. This is decreasing and this is decreasing, but this is decreasing to the asymptote and this is decreasing infinitely here, right? So noticing trends like that. Okay. And then obviously then the next progression from graph would be to look at a table of values here. All right. And personally for me, this is the most difficult one, looking at these tables of values. But if you're like me, right, you can always think about them in terms of how they would fit into an equation or turning these values into a graph, right? So those are kind of my two tricks there for dealing with this if this is a struggle for you. All right. But if we keep moving forward here, looking at these values, all right, we can turn them into points here. And what we can do is, again, try to imagine them as points graphed on a coordinate plane, all right? And so it would look something along this lines here, right? Something along this lines here. And then it's asking us to describe the function based on our table and the graph here. All right, so the answer that would have been really, really valuable here in terms of these relative points here is we can notice, looks like right now we have two relative max points and two relative minimum points, or it looks like it's kind of got a weird curved shape to it. All right, and we can notice that this is our minimum and this is our maximum, right, at this point. And so since we have a value going downwards and a value going upwards, this is probably a polynomial of degree 3 or 5, because it has to have an odd exponent, or sorry, an odd exponent for the variable, because it doesn't have the same ending behavior. All right. And again, this is going to be really, really, really important, is being able to paint pictures in your mind of what these graphs look like. And again, right now, being at home, you have the benefit of looking at your graphing calculator for everything. So please take advantage of it when you need it, right? But again, try to pick up some of these trends here in your mind as we go along. All right. And these are, again, more practice problems for you, so try them out and take a look, but being sure to dissect the entire thing, of course, starting with what is its parent function look like, right? And then painting that picture in your mind of what that parent function looked like, then going from there. All right. Then answering the question of vertical asymptotes, right? So you could just plug these very easily into your graphing calculator, see which one looks like it doesn't have which one does have the vertical asymptote here, or you can know some behaviors of these different graphs. So what does a logarithmic graph look like versus a graph with a degree of 5 versus a absolute value, right? That kind of stuff. All right. Then here again, really trying to take a moment to dissect what is happening to the function, especially, of course, look for the parent function. And since we're in this unit here, we're dealing mostly with logs and exponents. All right. So again, our base function for this guy is 2 base x. All right. Then looking here, all right, looking at the graph, I know it's hard, but if you had this, you could zoom in. But knowing it's got different behaviors in both the ends. So what does that mean? It looks like it's got a turn. What does that mean? And how does that relate in terms of the translations that may have happened based on its parent function? Okay. Going to the study guide here. All right, so really being able to just summarize what a function is. Hopefully by now that's second nature. All right, and how do we test for if it's a function? All right, how do we look for it in terms of a graph? How do we look for it in terms of our equation and in terms of our table? All right, then what happens to our functions when we translate them, reflect them, stretch, compress, flip them across an axis? What does that do to our different functions here? Okay, and then knowing that we have parent functions now, right? We worked a lot in semester one with some parent functions, but now we're able to add on our logarithmic and our exponential functions. We were able to add those into our little tool belt here. Okay, so then moving forward, we have our 311 checkup. We have our 3.11 checkup. All right, so couple quick problems here, right? It's asking you to identify the parent function. All right. Identify the parent function and then perform the translations that is being expressed to you. All right. Then here, of course, what's the parent function? What does that do to the graph? Okay, now we're looking at things in terms of asymptotes and in terms of our table values. Okay, then looking at the end behaviors or the extreme values for different functions, all right, being able to compare and contrast them. All right, then describing the relationship between the parent and the transform function, right? So looking for trends, seeing if you notice things, and then of course, when possible, plugging in values. All right, and oh, yep. So that completes 311. So obviously we have a quiz here. So far you have a quiz for 310, a quiz for 311. All right. 312, for the sake of time, I'm going to have you go over this on your own. But a reminder, this is just a recap of everything we've done here. Or sorry, this one, our review. This is a recap of everything we've done here. And always go here and do some of the checkup problems, because if you can do these checkup problems, it's a good indication of what's going to be asked of you on your test. All right. And you're going to take this 3.12.3 CST, right? You're only going to take the CST. Okay. Now, if you're looking for a place to pause, because it's been about a little over an hour, about an hour 15 here. All right. We just finished Unit 3. Okay, we just finished Unit 3. Okay, so my personal suggestion here would be stop, break, know that you're about a minute 10. Okay, you're going to be at about a minute 10 here. Okay, but pause, break, know that this is where we're going to start Unit 4. So this is where we're going to start Unit 4. And this would be a really good, again, like I said, pause point, make sure you finish all of Unit 3, get that done and under your belt, and then move on to Unit 4 here. All right, and I am super pumped about Unit 4, but for the sake of fairness here, I'm going to ride this out for the next 2 minutes. All right, so that at exactly a minute 10 here, you can come back and we'll start looking at Unit 4. So exactly at a minute 10 into the recording, we will start Unit 4 here. Welcome back at a minute 10. All right, so now we're going to move on to my personal favorite unit, statistical analysis here. All right, so to finish off the rest of this weekend here, we'll obviously go over the introduction for this unit, and I want to cover lesson 4.1 and 4.2 here. All right, so if we take an overview of what is statistical analysis, what are we going to be looking at here?
Batting average.
Apologies.
Who has the best batting average? Does this energy bar improve your test scores? Our life is filled with information and data. To understand it, we need statistics. Statistical analysis starts with data collection and interpretation. Gray wolves, nearly extinct, are coming back to Yellowstone Park. But how many are there? How are they affecting the elk and grizzly bear populations? Biologists use statistics to summarize data. In this unit, you'll calculate the mean and standard deviation for data sets and interpret these numbers to help you understand a population. What's the average age of moviegoers? Are 3D movies more popular with kids or adults? The motion picture industry uses studies and sampling to keep close track of movie-going trends. You'll learn to analyze data from a carefully chosen sample and draw conclusions about the entire population. Can dogs learn to read? What kind of evidence would you consider proof? This unit will show you how to design a proper experiment and how to decide if your data is conclusive. You'll also learn how to use simulations to decide whether sample results are consistent with a specified model. Do you ever read news articles like this? You'll learn to review published articles and critique their experimental design and conclusions. With some basic understanding of statistics and a lot of common sense, your arguments will be much stronger.
Okay, so that's a good overview of what we're going to look at for these units here. Okay, so we'll start off 4.1 with a review of graphical analysis of data. All right, and so we have a lot of graphical data always available to us here. Okay, and just a couple examples are tables showing numbers of banks that have failed, a line graph showing an increasing national debt, a bar graph showing the value of homes is going down, histogram showing the number of people without jobs by age group, right? So there's a lot of data always being flashed at us here, all right? And obviously, one of the problems here is how well do we understand what's going on, right? In terms of what are the facts telling us, what do the graphs really mean, and what are they really showing us, okay? So that's going to be a huge thing we focus on in this unit here. All right, so looking at a review of this data here, okay? So I like this example here because there's a ton of these kind of flashy ads, right? For things more than just obviously weight loss, right? Like make money quick, or have shiny teeth, or things along those lines. And something like this is an example where we have to look at probability versus statistics. Okay, so if we look at the definition, we'll get more into it, but probability is involves finding the likelihood of an event happening or not happening, right? What's the chance that this is going to happen, all right? Versus statistics, all right? So statistics involves collecting data, organizing it, right, and understanding what it actually means here, all right? So in order to figure out if the company is telling the truth, right, we're going to look at what's the probability, what's the chance that it's going to happen based on statistics here. All right, based on statistics. So in order to actually make this claim here that this works, they have to gather information, right? They have to collect their data, right? They have to collect their data in order to look at it and analyze it here. Okay, so again, there's two types of data here that we will really talk about: numerical data and categorical data, right? So numerical data deals with numbers, period. All right, categorical things deal with words or titles. So again, something like height is numerical, whereas hair color is categorical. So blood pressure can be a number, SAT score can be a number, population of a city can be a number, your salary is a number. But things that are categorical would be your name and your state, right? Those are a couple other examples here. All right. Then when we're dealing with statistics, right, the collection, study, and interpretation of data, we're going to deal with two kinds of statistics here. So descriptive statistics and inferential statistics. Okay, using data from a sample that can help you understand a larger population, right, versus our descriptive statistics, which we can use graphs or analysis to describe the data that has already been collected. All right, so inferential is talking about things outside of the sample set that we have collected. We're talking about making an inference or making an educated prediction. Versus, again, descriptive is talking about based on the data set that we actually have. All right. So if we look here, this is an example of a histogram. I don't know if you've been exposed to what a histogram looks like, okay? But it looks like a graph here based on a bunch of different boxes, all right, at different heights. And they can look a whole bunch of different ways here, but that's really what breaks this up is it's in little boxes. All right, it's in boxes based on categorical labels here. All right, and those boxes are at different heights based on their output values. All right, so if we look here, histograms showing right here, this is showing frequency and data distribution, right? So it's showing how frequent and the distribution across these different categories, right? So we have different categories. How are those distributed? Based on and based on the frequency of them. Okay. If we look at pie charts here, all right, pie charts are great for showing things as portions of a whole, right? So these are showing portions of a whole. All right, that's where it's taking away from another if it gets larger. All right, this is called a box plot. I don't know if you've ever seen one. Okay, a box plot. Again, how you know it's a box plot, it is shaped like a box here and it's got a line going through it. It could also go in the vertical direction as well. So you can imagine this just shifted up by 90 degrees here. All right, but box plots are really great as showing maximum, minimum, and these things called quartiles, right? And those are basically like the 25, 50, 75, 100 percenteth. All right, so it's good at showing these things called quartiles. All right, so those are the three that are going to be a little bit new to us here. All right, so then taking a deeper look at inferential statistics. All right, this is taking things, like I said, a step further. So instead of displaying the data, we're going to try to make a claim or prediction based on this, right? So you might hear this a lot on the news, right? We project that, or the projection is that that's an educated guess, right? That is an example of inferential statistics. All right. Also, car companies don't actually test the mileage of every single car that they build, right? They make a sample, they get the understanding, and then they're able to make a claim farther outside of that data set here. All right, and they can take, like I said, they can take a smaller sample then and test their theory and make sure that that theory is correct there. All right, so then here, if we're looking at fuel economy, it says the estimated fuel economy of this car is 27 miles per gallon. Okay, but your friend who has this car says she only gets about 24. The reason that this could both be correct is, one, they don't test every single car. So there is a little bit of error that might occur with this, right? There's a little bit of leeway, all right, in how accurate they are. The other thing is obviously there are other factors, right? Like Do you slam on your brakes? Do you coast more? Where are you driving? All of those kind of outside things could take effect here. Okay, now we're going to move on to talking about displaying our data. All right, so displaying our data. So no matter what kind of statistics is being used, right, the data collection is displayed in a way, or should be displayed in a way, for people to best understand it, right? For people to best understand it, right? If people can't see the data or get an understanding of what it means, then you didn't get your point across. All right. So there are obviously many ways to display data, but two simple ways here are to use a list or something that's called a frequency table. All right, so a list shows all values in our data, right? It shows all of our values, every single value that was collected. A frequency table keeps track of how many times each value has occurred, right? How many times each value does occur. All right, it helps organize a larger set of data where you've got repeating values. So if you look here, all right, this is showing about a range from 23 to 25 miles per gallon. All right, and it's showing every single time it was recorded. Look, first one, 23.5. Oh, so was the third one. Oh, so was this one. So it's showing every single value. This is our list example versus our frequency table. So if we split this up into categories based on their miles per gallon, we can count every time that 23 showed up. Oh, 1, 2, 3, all right, so on. So it's an easier way of organizing the data here. Okay, and that first one was a little bit easier because obviously there was only a couple numbers here, and they were whole numbers, right? So we looked at 23, 23.5, 24, 24.5, and 25. All right, but sometimes that might not really reduce down our values, right? Or the amount of data we're having to report out. So what we can do there is turn our frequency tables into classes, right? Into classes. So an example of a class here would be like a range, right? A range of weights, okay? So if we show our classes as a range here, we can call it an interval. We can call it an interval. And let me back this up here. All right, classes are just numerical intervals used to group data together. All right, so that's the formal definition of classes there. All right, so we're saying this is a range, 150 to 159. That's a range. We have two people in there, right? And this is a nicer way to simplify down data if you have too many values, because obviously if we went by every single weight, it could happen between 150 and 250. It's about, obviously like at least 100 points there. Okay. So we can then look here and we can make a couple things about the classes here. All right, so the last value in one class should not be the same as the first value in the next class. Therefore, what that's meaning is we shouldn't set up intervals like 150 to 160 and 160 to 170. All right, reason being, it can't be in two of the categories, right? It has to be just in one of those, right? So we want to set it up, okay, 159 is the starting number, so we go to 160, all right, to 169. And then we should obviously pick a class size that helps us best understand the data. All right, so if we wanted to be very specific with weight, we could do that. If we wanted to just look at if this was height here and we wanted to classify people as tall versus short, for maybe like the length of an apron, right? We could then just classify people into two groups. So you're less than this or you're greater than this, right? That range. Okay. Another way that we just were introduced to a couple slides ago to look at displaying values and frequencies is through the thing called a histogram. So taking a look at that histogram, right? It was those different boxes and it was used to show, right, that frequency of our different groups. Okay, so a key point here is it only uses numerical data and it shows the why values in terms of classes, all right, in terms of classes. And this numerical data then makes a bar graph, right? It makes a bar graph. So in this histogram here, all right, we are able to see our classes shown on the x-axis. We're able to see our frequencies shown on the y-axis here. All right, we're able to do a lot of ranges here, and some of the other characteristics of a good histogram is that we have, somewhere between 5 and 15 classes. If you get much more than 5, right? If you get much more than 5, much more than 15, right? It spreads this out too thin, it gets difficult to see the data. If we have less than 5, it looks like a bar graph, and it is more difficult to see trends there if you have less than 5. All right, another thing is no overlap between classes, right? So again, you cannot have an overlap. We got to make sure that each of the bars are specific, and you'll notice here again, it's a bar. All right, that's why there's such an abrupt change, because each bar goes with each class on the bottom. And then finally here, equal class sizes. All right, we have to have equal class sizes in order to make it look like a readable graph with general trends here, right? It would be very uncomfortable if this was, this tiny bar was from 150 to 159, but the next bar next to it was from 160 to 180, right? That wouldn't represent it the same because they're all the same bar size, right? So that's some good general tips here. Okay, then I'll let you take a minute here and look at our histogram above and answer which of these that apply for the data that's being shown here. Okay. All right, so a little bit more about histograms here. We can look at this thing called a relative frequency, right? We can display things as relative frequency. All right, so in this case, the height of the bar does not show the number of the individuals in that class, right? So it's not an absolute number of occurrences. Instead, it is relative, right? So instead, it's going to be relative, meaning that the percentage of the total data that falls into that class, right? So it's going to be out of 100%, right? It'll be out of 100% here, okay? So when we're doing relative frequencies, it's going to be from 0 to 100, 100 obviously being the total of the entire thing, all right? And when we add up all of these bars, of course, they should get us to 100 if we're representing our entire data set. All right. Moving forward here, something similar but different is a bar graph. Okay, so it's another way of displaying data here. And histograms are really great for showing numerical data, but bar graphs are also good for showing categorical data, right? Categorical data. All right, so bar graphs, again, look very similar to a histogram, but there's two major differences. Okay, the bar graphs don't touch each other. All right, and now the horizontal axes has to be categories instead of classes, right? Because again, classes are numerical, where categories are names or labels. Okay, and still the vertical axis shows the frequency or the number for each category here.
All right, and lastly, here we have STEM plots. All right, so this is another way of displaying the data. All right, and a STEM plot, what it looks like here is it looks like a table, and the left-hand column is labeled these stems here, and the right-hand column is labeled leaves. All right, and the stem is the first digit. All right, so if we look here, we've got digits between 0 and 5. Our leaves here, these are the second digits. So like if we look here, so the stem is 1, the leaf is 1 as well. So 1 and 1, that makes the number 11. Also 1 and 2, that's 12. If we go down here, we've got 23, 24, 25, 25, right? So we have a way of displaying this data here. All right, let's take a look at what a stem and leaf plot look like here. So obviously splitting apart, right? Stem is the first number, leaf is the next number. Okay, that's a pretty easy way of making a stem and leaf plot. All right, and this might be really useful when you need to show all of the data, right? But you don't want to write out every single value. It's a pretty quick way of condensing it, especially when you want to condense based on the first value there, right? In the 10s, the 20s, the 30s, 40s, etc. All right, so just to confirm here, blank uses graphs and tables to describe data that has already been collected. That is descriptive statistics, right? It's talking about data that has already been collected. All right, there was 2 types of data that we talked about, categorical and numerical, and there are 5 ways we talked about to display that data. All right, and here is the 5 ways, right? We talked about frequency tables, stem plot, histogram, list, bar graph. So really take a minute here to match these guys up, because you got to know, obviously, between the type of data, how does that actually correlate, right? What's the description that matches it? All right, and of course here, trying out some of these word problems here are going to be super helpful. All right. And the trick for all of these is obviously 1, read the entire problem, but then 2, look for the type of data display that you're going to be using here. So like first, here is a histogram, right? Then this one's talking about a frequency table, right? So again, that's really what's going to be helpful for you, is figuring out what type of data we're talking about, because then you can go to the characteristics of that table. How is that table made, and answer the rest of those questions. All right, so I'll let you try those on your own. Okay, and now, since we've looked at just one set of data here, the obviously the next progression there is how can we compare 2 different sets of data? Right, how can we compare 2 different sets of data? So if we look at this first example here, we've got quiz scores, all right, for 2 different people. So if we show the histogram for each of those, all right, we can clearly see that there's a difference between Paul and Dawn. All right, there's clearly a difference between Paul and Dawn when we look at the histograms from their data. Okay, and it's, when we look at their data, it looks very different, and the word we can use there is the distribution. All right, the distribution, and then if we click on the formal definition, it's how numerical values in a set of data vary. Okay, it's generally talked about with shape, center, and spread. All right, so if you look at the distribution of data, right, how each data set looks. Right, so if we look at both of these, and the 3 things that we're looking at, shape, spread, and center, okay, Paul and Dawn, they both have a shape, right? They both have a shape. They both have a peak. Obviously, there's a peak for both of those, okay? But Paul's shape is tallest in the middle, so it looks more like an equilateral triangle, versus Dawn, who's tallest here over in the right-hand column. Okay, center. Okay, center. So this is, we'll talk more about that soon here, but try to figure out, okay, well, between these data, it might be a little bit easier to determine what's Paul's center versus Dawn's center. All right, and then this thing called spread. So again, obviously, how wide or how far out is all of the data? And Paul here goes from 40 to 90. So Paul has more spread out scores, while Dawn, majority of her scores here are between 70 and 99. Okay, And we'll talk, obviously, of course, more about these three in detail. All right, so the next thing is another one called modality. All right, so to describe the modality of a distribution, we look at how many peaks or modes there are, right? So again, it's a method to describe the distribution, right? So how is the data displayed? All right, it's called modality. And the reason it's called modality is because we're going to look at how many peaks there are. Another word for peaks is this word called mode. All right, so if we look at a mode, it is the value that is expressed most often in a data set, right? Mode, most often. Okay, so looking at the modality here, there are three types that we're really going to talk about: unimodal, bimodal, and uniform. Okay, so if it's unimodal, it has just one peak, right? And you can see here clearly there's one peak. If it's bimodal, right, it means that there's two, right? Bi meaning two, okay? There's two clear peaks or two clear modes. All right, and then finally here, the last one is uniform. Okay, so clearly we can see there's a lot of different modes. It's really hard to tell that there's not just two specific ones. Okay, so looking at these guys here, the data set blank is unimodal and the data set blank is uniform. Okay, so if we were to look at these values, I'm going to go with that one is uniform here. We have to take a look between these values here. So if I look, all right, clearly with this one, I've got three values at 4 and nothing else beats 3 values. Versus if I look over here, I've got my 2 with 4 values and my 6 with 3 values. So this one would look more bimodal. All right, so this one it's got to be my unimodal, because again, if I were to write this all out, 4 is the most frequent and nothing else is close to that 4 value. All right, and then obviously 3 would be uniform because all of the values are at that one point. Or again, if they were equally distributed between, maybe a 1, 2, and 3, that would work as well. Okay. So now we have to look at symmetry, right? So symmetry, and we obviously talked about this a lot with graphs here, but there's symmetry with statistics too, okay? So we're going to look at two symmetric sets of data, all right? The left one has this unimodal, right, that one peak, and the right one has this uniform distribution, all right? And if we flip them over, right, if we flip both of them over, right, they look relatively similar to the original. Okay, and obviously this first one here matches up perfectly. This one, if you look really closely, you can see like there's a slight difference between some of them. All right, but as a whole, right, it matches up pretty good. Okay. Oh, sorry. So that would be a symmetric. Those would be symmetric graphs, right? Because if again I flip them, so that's what we talked about a lot graphically, is when we flip them, right? If they are lined up perfectly, right? That's talking about it's symmetric about both sides of the graph. All right. But now, if they're not symmetric, they can have this thing called a skewed distribution. All right, a skewed distribution. And what that means is that the tallest part, right, the tallest part is moved to one side or the other, right? It's not perfectly in the middle, okay? And if we look at this, if the distribution has a tail or lowest side to the left, it's called skewed left. All right, so what does that mean? Look at this. Okay, all right, we have a peak. Right, we have one peak, so we know it's unimodal. All right, but it builds up and it has this what we call tail, because it's obviously longer on this way. So what we call this is skewed left. All right. Then we have this guy who's skewed right because of the same thing. It's unimodal, right? Majority of our big peaks right here are on the left-hand side, and we have our tail on this right-hand side. So we say this is a skewed right graph. All right, and then if we look down here, we have a bimodal. And we have our bimodal, which has our 2 peaks. Okay, so obviously if I flip these graphs over, we're going to notice they don't match up as nicely, right? They don't match up as nicely. So these guys would not be equally distributed, right? Those are our skewed graphs. They're not equally distributed. All right, moving forward to STEM plots, modality, and symmetry, okay? So we can look at STEM plots and figure out the exact same things. Are they unimodal, bimodal, or uniform? Are they symmetric or are they skewed? All right. So if we look at these, the question is how do you know? Okay, how do you know? And firstly, what I'm going to look at here is, do you notice how it kind of looks like a histogram turned sideways? It kind of looks like a histogram turned sideways, right? Because this one here, all these numbers are even and look like they match up really nicely. So to me, that's going to be uniform and symmetric, right? That's going to be uniform and symmetric. Now, if I look at this one here, it looks like it has 2 peaks. It looks like it has 2 peaks. So it looks like it is bimodal. And if you look at the peaks here, if I were to flip these over, they look like they match up pretty closely. So they look like they're bimodal and symmetric. All right. And now we got to look at these 2 here. All right. Both of them are unimodal, right? And one of them looks like it has a tail more than the other. So if you look here, right, these values, this would make our tail here. All right, and since the tail would be on our right-hand side, it's going to be our skewed right graph. And that's going to make this one our unimodal. I don't know what they mean by mostly, but probably mostly symmetric. All right. Woo. All right. So that I just looked at this and treated this like it was a sideways histogram. All right. So that's one way of looking at that. Okay. So again, we've talked about the mode being the peak, right? The most often valued, the one that you see the most. All right. And again, if this is your first introduction to statistics, welcome. If not, these words will sound familiar to you. We're going to talk a lot about mode, median, and mean. All right. Mode, median, and a mean. So mode, again, is, of course, where it has the highest peak. It is the one that is used most often. It's the one that's used most often. Okay, so obviously it's easy to find that because it's the highest peak there. All right, it's always the highest peak. When we're talking about median, okay, we're talking about the absolute middle value. All right, we're talking about absolute middle value. All right. And to give the formal definition, it is the middle value in a data set. Half the values are above and half the values are below. So if we start out here not graphically, okay, not graphically, if these are our numbers in our set, 2, 5, 6, 10, 12, 17, 25, okay, to find the median, we find the number in the middle of them. Okay, so there is 7. Okay, there's 7 values. All right, so what we're going to do is we're going to look for the 4th value in this number set. And the reason that is because if I look at 10 here, I have 3 numbers to the right of it, and I have 3 numbers to the left of it. So half of the values are below, and half of the values are above. So 10 here is my median value. 10 is my median value. Okay. if we look here, right, if our histogram was broken up by specifics here, okay, our median is of course going to be halfway between the values. All right, so if we look here, there are 35 values in the distribution. Again, of course, counting this block as 1, 2, right? And each block counts as 1, right? So there's 35 values, all right? And we need to go where the value, where there's 17 values below it and 17 values above it, right? That middle value there, okay? And in this case, right, if we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, right? We're going to be in this 5 column. We're going to be in this 5 column. Same thing, we could have counted 17 the other way, right? But we were going to end up in this 5 column. All right, same thing this way. All right, same thing this way. So if we look at our graph here, okay, we have 20 values, so we have to find a value where we have, 10 above, 10 below, right? We're trying to find that midway point. And for this one here, okay, you're going to notice that it's a little bit outside of the middle of the graph, right? Like this one was exactly in the middle, as you would think, between 1 and 10. It's going to be somewhere around 5. Maybe this one is a little bit more to the left here. And of course, that's the part of the reason is because of the size of the bars over here, right? This is such a large bar that it might add up to, all of these little ones put together. Right, so again, it's not about location, it's about actual values. All right, and then when we look at our mean, right, they can say it as the center of gravity. It is basically the average, right? It is also called the average. So what it is we take the sum of each value and we divide by the number of values. All right, so by that, if we have 8, 9, 10, and 20, okay, there's our 4 values. All right, so we would add them all together, we get 47, and then we divide by 4. And what we can say then is the average number of all of those is 11.75. Okay, so if we take a look here again, mode is our peak, median is half below, half above, right, our halfway point, and our mean is the balance point. All right, mean is the balance point. And no, right, no, it does not have to have the median always be the mean, right? Or the median doesn't always have to be the peak. All right, it doesn't mean they can't be, right? The same point could absolutely be potentially all 3. Right? But that would just depend on the data set that you have. Okay, so looking here, sometimes it's difficult to figure out these by eyesight. All right, but we can try to take a look here. All right, this one is unimodal and it is perfectly symmetric. Okay, so since we know it's unimodal and perfectly symmetric, okay, that means that our mode here is at 5, right? It's one mode. And since it's perfectly symmetric, this middle point here is going to have half above and half below. So this is going to be our median, right? This is going to be our median point. And we're doing our mean, which is also the balance point, right? And so for this one, again, our balance point is going to end up also being 5. Right, so this is a perfect example of where it's all at the same point because, of course, it's symmetric, it's unskewed, and it's unimodal. All right, if we look at this one here, all right, if we look at this example, the mean, right, our mean value is going to end up actually being in this smaller box here. It's going to be in this smaller box here. So if we actually take a look at this graph that we looked at, all right, this is our mode, right? This is our mode. This bar contained our median, right? This bar contained our median, and this bar is actually containing our mean, right, or our average. Okay, so again, there's a lot of different differences, but knowing the definitions is going to be what's really, really helpful for you. Okay, and the mean is often called the average. That's always a good thing to remember. Okay, so then moving forward here a little bit, we've got range. Range is talking about the spread of our distribution, right? The spread of our points. Okay, so that if we look here, both of these are unimodal, both of these are symmetric, they have the same center point. But if we look at this first one here, it obviously looks a little bit more spread out, right? Or it's wider, right? It's wider. Versus this one where it's all bunched together. So when we're looking at our range here, we can look at the difference between our smallest and our largest number in our data set. So if we look here, we've got a 9 and a 1. So we can look at the difference, and that's going to give us a range of 8, right? So we cover a range of 8 there. Versus here, we have 6 and 4. So 6 minus 4, we just have a range of 2. So obviously, this distribution is going to be a lot closer together. All right. And then what we can do, another way to measure the spread of our data is to look at this thing called our standard deviation. All right. So if you want to get a little bit more advanced than just looking at our range, we can look at standard deviation. Okay. And standard deviation is a typical distance of a data value from the mean. All right. So it's going to take a little bit more than just this introduction unit, so we'll save that for later. But basically, again, this is all determined based on the mean and how far away you are from the mean here. All right. So then here, if we look at our histograms we talked about for Paul and Dawn, we can notice here obviously a lot more things. We can talk about the mode, we can talk about the range, we can talk about median mode, we already said that, but median and our average. And we'll learn how to, of course, calculate those guys later here. All right, but what we can notice here is this thing called an outlier. All right, and what an outlier is it's an extreme value that is not close to the other values, right? It seems out of place. So if you look here, all of these are kind of close together. They're touching, right? They kind of look like a nice graph. All right, over here, we start going to the left. It's like they're all touching, they're all close together. We skip a couple, then all of a sudden there's a value, right? So this guy kind of just looks like an outlier or like a little loner all by himself here. He looks out of place in this graph. Okay, so again, you can take a minute to look at that on your own and really dissect it, but it's going to be super, super helpful if you can walk through those problems here. Okay, so then if we look at this entire thing here, okay, so we were using inferential statistics, or talking about inferential statistics, and what it does is inferential statistics uses a small group of sample data in order to make a claim or prediction about something larger, something in the future, right, to make a prediction. All right, and this is usually done when gathering data for the entire population is not practical, right? So for example, if we wanted to get something at St. Lawrence, right? If there's 800 students, right, it may be possible to get the opinion of every student, right? That would be pretty simple. But if you wanted to get something for the entire state of Illinois, right, it might not be possible to get the opinion from a couple 100,000 people, right? So we might get a sample set and look at that. All right. And so here it says, for instance, imagine how hard it would be to ask every person in the United States what brand of toothpaste. Okay, obviously. But now if we go back to this example here, pretend that Dawn and Paul are representative of two different history classes. Their quiz scores and their quiz scores are shown in the histogram below. All right. So what is the problem? What is the problem of using this student to represent an entire class? Okay. The problem is that this student's average might be far from the class average, right? So
Paul might be an average student in his class while Dawn is the superstar, right? So Dawn might not be a true representation of the rest of the class. Or, of course, Paul might not like history or might not be his subject, so he might be struggling a little bit more while everybody else in the class is excelling. So you would need several students, right? You would need to look at several students and see how students in the same class look, okay? And we'll obviously talk more about that later here. All right, but if we look shape, center, and spread are characteristics of, distribution. Okay, distribution. All right, and then taking a look at obviously all those different characteristics. What do they mean? What do they tell us about the distribution? Okay, and I'll let you practice these here. But again, of course, as always, picking up on trends in graphs is going to be super important for us. Okay, and there is a lot of practice because we just covered a lot of content. So again, please take your time, make sure you go through it and try these out here. All right, and again, noticing everything that you can about these graphs and really just paying attention. I think that's kind of going to be the biggest thing here, is paying attention and knowing what graph you're dealing with or what representation of your data you're dealing with. Okay, and obviously, we've talked a lot about histograms, and all 4 of these questions are about histograms, so that's kind of like your major one that you need to make sure you feel confident with. All right, but obviously we can't ignore the others, right? The bar graph, the frequency, the stem plots, we've got to be able to pull all of those. But moving forward, looking at our study guide here, okay, and this is going to be super important, right? So talking about the difference between descriptive and inferential, talking about our data being numerical or categorical, right? Really being able to use some more descriptive words when we're talking about the data that we want to collect here. Okay, and then talking about our data displays here. Okay, we've got list, frequency table, histogram, bar graph, stem plot. Okay, and really understanding what type of data can we look at and what is the descriptant? What of those, what's like an example graph look like? Okay, and then talking about the distribution of our data. So we've talked about modality, symmetry under our shape. Okay, we've talked about our center, our mode, median, mean. Okay, looking at different center points, and then looking at the spread, right? So our range and our standard deviation of those. Okay, so then actually looking at an example of a graph, right? So again, unimodal because there's 1, bimodal because there's 2, uniform because they're spread across. Looking at the shape, right? It has the tail left, so it's skewed left. No tail, symmetric. Tail right, so skewed right. Looking at the difference again, mode being the peak, median being half above, half below, and mean being our center of gravity, right, our balance point. And then something new that we're going to deal with is standard deviation, okay? But this picture does a really nice job of showing you the difference between this entire thing, right, we said was our range, so it's the difference between our smallest and our largest. And then looking at this thing called standard deviation, which is distances based off of our mean value, right? Distances based off our mean value. Okay, so this was a long unit here. There was a lot of pages, so again, take your time with this. But if we go to our checkup, of course, I always believe this is a really good test of whether or not you really understand it. And of course, this one's going to ask you to do some basic calculations here. Okay, so pay attention to those. All right, and for frequency, okay, so for frequency, with this guy here, right, it's a percentage of the whole. It is a percentage of the whole. So if you count up all these values, there's 50 values total. Okay, so whatever value you're calculating is that number over the total, times by 100, right, because we've got to make it into a percent. All right, so just try to keep that in mind there when you're dealing with frequencies. Okay, and then obviously being able to look at a sample data set and imagine it looking like other graphs here, that's going to be really helpful. So building a histogram or building a stem plot, okay, that will be very, very helpful.
All right, same thing, looking at histograms here, like we did in the last lot of slides, talking about the major characteristics of those graphs. All right, and under this 4.1, we have two different quizzes. So we have, in general, types of data displays, right? So that's going to obviously talk about the difference between the major types of data displays, what are the different types of data, all of that kind of stuff. And then the second quiz, the 4.1.4, right? This is going to talk about actually analyzing the data. So again, more towards the end of this study, right? Our mean, mode, median, all of that kind of stuff. Okay, so for 4.1, oh, sorry, you have both of these quizzes here to try to finish up. And then last lesson we're going to cover this weekend is this 4.2. Okay, we're going to cover 4.2, which is review of numerical analysis of data. All right, so again, it's another longer one, which is why I set it for the weekend here, but let's get rolling. So review of numerical analysis of data. All right, so we just talked about a histogram. And now what we're going to do is we're going to start talking about this thing called central tendency. Okay, central tendency. And the formal definition of that is the degree to which the data are clustered at the center or of a distribution or our data set, right? So again, what does the clustering look like? Okay, so what does the clustering look like? That's what we're talking about with central tendency. Okay, so we just talked about our mean, right? We just talked about our mean, and that is part of our central tendency, right? So what is that data doing towards the middle of our graph? All right, and so mean, right? We talked about it being our average value, right? Our average value. So what we can do here is we talked about it in general, but what we can do is we can have a mathematical equation to talk about mean. All right, and this symbol here, x with a line over it, can be used to represent the mean, and it's also read as this thing called x bar, right? Because x bar. Hopefully it's pretty obvious. All right, so we can calculate it like that. All right, so then if we look, the formula of the mean can also be written using these different symbols. All right, so again, x bar being our mean, so it's like saying take all the individual values and add them up and divide by the number of values that there are, right? So we talked about that. So if we look at our mean of our data set, we take all the individual numbers and we add them and we divide by the total number of data points that there are, and there was obviously 6 values, so we divide by our value of 6. So our average is 29, or our mean is 29. Okay, so then we can look at this thing called sigma notation, right? We can rewrite it in this form of sigma notation, all right? And we did get introduced to this here, and this is, again, what's going to take it from being more basic into being more stepped up in preparation for, things like a pre-calculus, all right? But we can use this sigma notation to represent our value set here. All right, and what this is our x bar, which is our symbol for mean. And what this is saying is this big guy here is saying the sum. All right, that's what it's saying. This little sideways Greek E, right, our sigma, this means sum. All right, this means the sum. So you're going to add together different points here. All right, and what it's saying is we start with I, right? We start with this bottom, so I starts at 1. All right, and we go all the way up to whatever value n is, right? So if we're going for 5 values, we put a 5 there. Okay, and what this is saying is x of I, right? So remember we talked about it, x of I, so this would be x1. Then if we kept going, we'd say x2, x3, x4, x5. Right, all the way up to our n equals 5. So this is saying is the value, and x1 would be the first value in the data set. It doesn't have to equal 1, but it'd be the first value in our data set. All right, and then since we have this here, it means the sum of all of that. So again, we would add all of these guys together. And then hopefully you notice here that we have this coefficient or this constant here out front,
It's going to turn into a coefficient of 1 over n. It's going to turn into a value of 1 over n, which means once we take our sum, we multiply it by this 1 over n factor. And of course, n here is going to be the same as n there. All right. So if we look at what this means using the same data set from before, okay? So notice this is going to be term 1, term 2, term 3, term 4, term 5, term 6. Okay? Again, assuming that these are written in number order, which they are, right? That's an important piece here. They have to be written in in order from lowest number to highest number. They have to be written in the correct order. But looking here, starting with our sigma notation formula. So if we start with that formula, okay, that's just a given formula here. All right, we substitute in 6 for n because we have 6 values here. So notice we put our 6 out in front, we put our 6 on top of our sigma sign, which means we're going to include all of our points. We're going to include point 1 through point 6. That's what this means here, point 1 through point 6. So point 1 through point 6. All right, then what we do here is we plug in all of our data in the x column because we said we're going to take our sum here, right? That's what that means. This is saying the sum of the values 1 through 6. Okay, so that's what you read that, the sum of the values 1 through 6, where all you're doing is having the value itself, right? You're just having that value. So x of 1 is saying, what's the value for the first point? Well, it's a 4. X of 6 is saying, what's the value for the 6th point? That's 53. All right, so we're going to replace our sigma notation, right, with our summation. So we're going to show all of those points getting added together. All right, once you add those up, you divide by 6, you can simplify, and you can write it as x bar equals 29. So again, showing you another way of writing the same thing, x bar equals 29. We just took the average of our entire data set, right? And where this is going to be helpful is if we don't actually want to look at the entire data set. Maybe we only want to look at the first 3 values, right? Now we're not taking the entire data set. Again, we're only taking a small portion of that, and we can still write that using the same notation here. All right. Looking at our median here, all right, our median. The median is the middle value when all values are arranged, again, from smallest to largest. That is going to be key. You have to arrange them from smallest to largest. All right. It's very, very easy when we have an odd number of values, right? So looking here, we've got 1, 2, 3, 4, 5, 6, 7. Sorry, we've got 7 values here. All right, so once we rearrange them in order from in order from smallest to largest, there we go. All right, 11 is going to be my middle number because it's got 3 values below and 3 values above. All right, the issue becomes when we have even numbers, right? If we have even numbers, when we rewrite them, okay, we've got, for this one, we have 2 middle values here. All right, and so what we have to do is then we have to take our average of the 2 middle values. So we have to take and add them together and divide by 2. So our median here is 19.5. Okay, it's 19.5. And again, the reason because is that I've got 3 below and 3 above, well, I can't split these, or I can't just choose one over the other. So you add them together and divide by 2. All right, and that's all dependent on the number of values that you have. All right, so now if we want to take a look at what is really the difference between mean and median, all right, because I know they're both talking about the central tendencies. Sometimes they even are the same value, right? Sometimes they are the same value. All right, but again, with our mean, we're talking about our average value, right? Our average value. With our median, we're just talking about the value that's in the middle, all right? The value that's in the middle, right? It doesn't matter numerically what that number is. It's just halfway between your data set, all right? And where this is going to become important here, talking about our data set, is because we have this thing, again, called an outlier.
right? An outlier where it's far away from the rest of the data. Okay, so if we look at something, right, this data set is exactly the same, except for this one over here has this thing called an outlier. All right, it has a thing called an outlier. All right, and that outlier is very, very far away from the rest of the data set. Okay, and if we look without our outlier, okay, our mean is 9 and our median our mean is 9.2 and our median is 9, right? Halfway between the data set is 9, and if we add them all up and divide by 5, we get 9.2. All right, if we add an outlier, you're going to notice it has a more dramatic impact on our mean than it does our median. It has a more dramatic impact on our mean than it does our median. Because, remember, median's just talking about what value is in the middle of the data set. Versus mean has to add all of these together and then divide by the number of values. So the mean is really, really dependent on what the actual values are, right? The weight of those values. Okay, so again, there we go. The median depends only on the order. The mean depends on all of the data, right? So the outlier can affect a mean really, really differently. Okay, so if we have a left-leaning outlier, right, it will shift. Our median stays here, right? So at 79. But our mean, our average value, will shift more towards the left, right? It'll shift more towards this outlier. And when we have a right outlier, notice it's going to shift our mean more towards that right outlier, right? Our mean shifts towards the outlier. If we have it random, right, then of course mean and mode mean and median are pretty close to each other. But look, so again, if I go here, if I add a right outlier, it shifts everything. If I add a left outlier, it shifts it the other way, right? And again, the mean gets pulled towards whichever outlier I have, if I have an outlier. All right. And then finally looking at the central tendency called mode. All right, so this is the one that occurs most often in a data set. All right. Again, mode, you can have more than one mode. It can be found in both numerical and categorical, and there could be no mode, right? There could be no mode as well. And then this is one that's really, really important here. Okay. Since it doesn't deal with actual values, right? It doesn't determine, doesn't depend on the values here. Okay. It can be found using both numerical and categorical data. Right? Numerical and categorical data. All right. So looking at our data sets here. All right, if we look at our different data sets, okay, so obviously here for the mode, the number that's used most often is 45 because it's used twice. All right, this one, we have two modes, 4 and 9, because they're both used 3 times. And then same thing here, right? So we can have multiple. So blue's listed twice, green's listed 4 times, and hazel's listed twice. And so is brown. So obviously green is listed 4 times, green is listed 3 times. Apologies, I counted that one. But green is listed more times than the rest of them, so green is our most often represented data. Okay, so the measure of central tendency numerically describes the, center. All right, so the central tendency, of course, describes the center, and what we're talking about most was mean, mode, and median. Okay, so that would be the 3, and then looking at sigma notation, right, I don't want you to get uncomfortable with that, right, so you got to at least look at it and try to familiarize yourself with it, so if you see it, you know what it means, but don't hyper stress on that one. Okay, Then, of course, you're being able to answer some of these questions, but my trick for you is make sure that the values that you're given are in numerical order. Don't just look at the first three, right? Make sure they're all in numerical order before you get started, because that's going to make a big difference. Okay, that's going to make a big difference when you're doing some of these calculations. So a good habit is just make sure it's already in the correct order to start with. Okay, same thing. Look, what is the mean of this data set? All right, well, for mean, it doesn't super matter, but if this was median, right, or it would be it'd be a little bit more difficult because you'd have to figure out the order of these values. So what I personally do here is I start out and I rewrite this problem. I look for the lowest value and I write them all out in the new order. All right, same thing. Mean, mode, right? It's going to ask you with random data set. So the trick there is to make sure you put them in order first. All right, so again, then remember this thing called range. It's one way to measure the spread of the data. All right. And there's another one that we can look at here, and it's called quartiles. All right. So a quartile, the definition of that is a little, I wish they would have written this better. Okay, but basically a quartile is we can split up our data into halves, right? So a median divides it into two halves, right? We've got a left half and a right half. Now a quartile divides the half into halves, right? So it divides one of the halves in half, or it again divides the entire data set into quarters, right, or fourths, right? And that essentially means we're taking our data set and we're dividing it into 4 parts, right? 4 parts. Okay, so in other words, the quartile is the mean of one of our halves here. Okay, so oh, it's asking. I thought I just read the click on a number for a second. That was pretty funny. All right. So if this is our median, right, 10 is our median, we're then going to split 10 in half, right? So 8 is halfway between our 2 and our 10 because we've got 2 values here, 2 values there. All right, so our values is in the first quartile. All right, and I don't know why they picked this one. We'll keep moving with quartiles here. So perfect. Let's look at these better examples. Okay, so when we're looking here, all right, so it starts with, of course, finding the median and then splitting that in half, right, to find the first quartile, and then splitting the right-hand side in half to find our third quartile. All right, so if we look at these examples here, it'll make a little bit more sense. All right, and obviously the first one has an odd number of values and the second one has an even number of values. As we found out, obviously the odd numbers will be easier because we can find middle points, at least for the first value here. So let's take a look.
First, let's find the median. The median is 20. Now let's find the first quartile. The first quartile is 14. Now let's find...
Okay, again, we found the median, so this now becomes one of our halves, right? So these data set becomes one of our halves. This data set becomes our other half, right? So we have to find, again, halfway, like in terms of just numbers, right, between these values. So 14, because there's 2 here, 2 here. All right, so again, that's our first quartile. Same thing's going to happen on this side. So hopefully you can start to notice here I've got 5 values. All right, I've got 5 values. So when I'm looking, okay, 25 is going to be my halfway because I got 2 and 2.
Find the third quartile. The third quartile is 25. First, let's find the median.
Okay, and I really like the way that they do that. They count it down because that's what I do in my head sometimes, right? I'll personally have my fingers. Like, so I'll start with one finger on the right and one finger on the left, and I'll move my fingers in to track, which values I'm at, the same way that they are doing with the shading.
Okay, but obviously notice here that when we get to look for just our first median, okay, when we looked at our median, we're going to have two values. Okay, so we've got to take the average of them, right? We're going to take the average.
The median is 21. The average of the two middle values, 20 and 22.
Okay, and the reason we got that was because we had to do 20 plus 22 divided by the number 2 since there's two values there, and that's how we get 21.
Now let's find the first quartile.
Okay, so again, starting with all right, back up there.
Find the first quartile.
Okay, so if you notice here, we now added a 21. Okay, so we added a 21, which is between those two. All right, so when we go and we start counting for the first quartile, notice now that they actually included that 20, whereas in the odd example, they did not include the median. All right, and there again, the reason being is that this median is this arbitrary number 21 that's between these two values. So we don't treat this 20 as it's in the median or like it's in the median. Okay, so then we're going to count these down. And again, I really like the way that they do this with shading. Okay, so then of course, when we count them down, 20 and 1 cancel, 19 and 4 cancel, 15 and 7 cancel. So we're left again with two values in the middle.
The first quartile is 8.5.
All right, it's 8.5. And hopefully you know why, because again, we're going to take the average. Okay, we're going to take the average.
The average of the two values, 8 and 9. Now let's find the third quartile. The third quartile is 34.5. The average of the two values, 32 and 37.
Okay, so that was two examples of how to manually look for these different quartiles here. All right. Then we can do what's called the 5-number summary. Okay, the 5-number summary. All right, so basically what we can do here is we can look for 5 different points, and that will help tell us a lot about our data set. All right, so the first one here is our min and our max value. So what's the absolute lowest? What's our absolute highest value, right? So min and our max. All right. And then the one that we've been talking a lot about is our median. So that's going to be the number that is in the middle between your mean and your max. All right. And then we just learned about a new way of calculating two new values, right? And those would be our quartiles. So we have our first quartile, which is quartile 1, and then we have our second quartile, which is quartile 3. All right, so if we were to look at this, right, if I had these 5 points, it will tell me a lot about my graph here. All right, so if we look, 2 is going to be our minimum, 3 is going to be our maximum, 10 is going to be our median, right? It's halfway between these values. All right, so then if I look at this set here, okay, halfway between is going to give me 8 as my first quartile, looking at 14 through 28, right? 17 is going to be halfway between that, and that's going to give me my third quartile there. All right, and again, that tells us a lot about our distribution. All right, and then if we look at that, right, we can do what's called a box and whisker plot. All right, and the reason it's called box and whisker because look, there's a box here, and these things on the outside we like to call whiskers. Okay, so a box and whisker plot. All right, and this is a really, really good way of showing a summary, right? It shows the summary. And the box is made up of our first quartile, our median, and our third quartile. And that makes up our box. And then we have our whiskers reaching from that box to our min and our max value. Okay, from our min and our max value. All right, and something we need to highlight here is that when we plot this box and whisker plot, all right, sorry, we have to show this as if it was on an actual number line, right, or actually on a graph. All right, so we can't just skip values. All right, so you're going to notice here we've got 2, 3, 4, 5, all the way up to 28, and they're equally distributed numbers. All right, and what happens is we then modify the basic box plot to fit the values that we have, right? To fit the values that we have,
right? And you can notice here it's very skewed, right? It's very skewed. It looks like we've got a very small first quartile, a very large third quartile, right? And even farther max value, right? This whisker here is huge, right? It reaches really far this way, where the left side looks a little bit more compact. All right, and obviously that tells us a lot about our data that we're looking at. Okay, and we'll talk obviously more about how to analyze them here, but how you draw them is, okay, first you're going to, of course, be on a number line, all right, and you have to draw this, again, equally spaced away from each other. All right, so that's I guess step 0 is to remember that. Step 1 is we got to find our 5-number summary, right? Give us those 5 points. Second, there we have to draw our number line or use a number line that we have. All right. Then we have to draw the box, right? The inside box with our 2 quartiles. So quartile 1 is the left side, quartile 3 is our right side. Then we draw our line in the box at our median. All right, and then we create our whiskers again to, of course, show the left and the right here. Okay. So then looking at this data set here, okay, looking at this data set, you would have to find those potential 5 points here. Or just notice right now that this is only giving 5 points. So those are the 5 points that we're going to talk about. All right, and trying to pick up on some general information here. All right, so if you look, we've got a 2, 7, 8, 9, 10. All right, so what I notice here is that 7, 8, 9, my box in the middle is very uniform and even, right? So I'm going to be dealing with a very uniform, even box there. All right, and then I've got 10 here, which is also very, very close. Okay, so I believe that it's going to be here because, again, 7, 8, 9, 10 are all 1 space away from each other. So if you look here, it looks like 1 space, even space, even space. And our far whisker over here is way farther away than the rest of them. All right. On the opposite end of that, if we look, we've got an example here. We've got 20, 26, 27, 35. All right, and then a really far whisker. All right, and it's got 2 graphs that it could possibly be. If we look at 12, 15, 16, 17, 25. All right, so again, 15, 16, 17 are all perfectly 1 space away from each other. 25 is still a pretty far outlier. All right, and so again, 15, 16, 17. So when we're making our box, 15, 1 space, 16, 1 space, 17. So that's going to be right there, which means that this guy is, of course, going to match up to there. And when we look at our data, it makes more sense because, look, we've got 16 and 17, which is 1 space, but then between our median and our third quartile is a larger number, right? Is a larger gap jump from 27 to 35. All right, and then finally here we have 15, 18, 20 as our box. 24 is our whisker, so it's not all super close, but it's also not very far away. The main point that's far away here is our minimum value of 1, which is how we get to that graph there. Okay, so again, take a minute, actually work yourself through those data and how did we get there. Okay. So then we can look at this thing called the interquartile range, okay, the interquartile range. All right, and again, our range is talking about a set of data. So if we're looking at interquartile, all right, it's the distance from Q1 to Q3, all right? So now, instead of looking at the entire range of our data set, right, we can look at our interquartile, or the range between our quartiles. All right, so our overall range would be 28 minus 2, right? So that would be a 26. But now if we're looking from quartile to quartile, we're looking at only 17 minus 8, which gives us an interquartile range of 9. Okay, and the interquartile, how is it displayed on the box plot? Okay, it's shown as the width of the box, right? So this overall width of our box shows us this interquartile range, while our entire box plot shows us the range, right? The whisker, from whisker to whisker, shows us our entire range here. Okay, and so represents the middle portion of our graph here. Okay, and looking at the interquartile range, right? If this is a very large region, right, or a very wide region, we can assume that it's not very close around the data set. Versus, again, if this was really close and really tight in a very small interquartile range, it would tell us that all of our data is very, very close to this median point or this middle point here. Okay. Then when we look at our interquartile range in the effect it has on outliers, all right, it is going to be super, super important and helpful when we are determining if something is an outlier. Okay, so if we look here at our graph, we have a max value that's very, very far out away from the rest of it. And you can tell either by looking at the numbers or just by looking at the box plot how long this whisker is. All right, how long this whisker is. It's very far away from the rest of the box plot, and this interquartile range is very far away from. Okay, and so what we can do then is we can use this test. It's called the 1.5 interquartile range test. All right, and what that does is it helps us be able to determine if a value is an outlier. Okay, so what we can do is we have our 5-number summary. All right, we have our 5-number summary. What we can do then is we can find the interquartile range. All right, so our interquartile range is 11 from our third quartile to our first quartile, or vice versa. All right, so then what we can do is we can find 1.5 times that interquartile range. So 11 times 1.5 gives us 16.5. All right, 16.5. So then what we can do is to find any low outliers, right? So any values that are below our box, okay, we can use this equation where it's Q1, so quartile 1, minus our 1.5 IQR, right? And that's going to give us the value here. And what it's going to say is, and we do that, negative 12.5. So any value lower than negative 12.5 would be an outlier. So if we had a negative 15, that would be an outlier. Okay? And the only difference between looking at quartile 1 and quartile 3 is now instead of subtracting, we're going to add, right? So we're going to add to quartile 3 our 1.5 IQR. Oh, let me back that up. All right, so then when we do that, here we add our 1.5 IQR to our third quartile of 15, and we get 31. So it's saying any data above 31 is an outlier. So lo and behold, 33 here is going to be our outlier. 33 is going to be an outlier. And if we look at our full data set and not just this 5-number summary, if we had a 32 or a 32.5 or a 35, right? Well, we couldn't have a 35. Sorry, I lied to you. We couldn't have a 35 because 33 is our max number. But if we had other values between 31.5 and 33, right, we could also say that those were outliers. Okay, so what we would do then is we could modify our new box and whisker plot. All right, I would show you this if we were in person, but there are some programs that automatically do this kind of stuff for you, right? And so being familiar with these notations, especially when you're looking up graphs, is going to be helpful. All right, but basically here, our original box and whisker plot looked like this, all right? But we determined that this point here for 33 was going to be an outlier. Okay, was going to be an outlier. So what happens then is in this modified box and whisker plot, it represents our outlier point as a dot. right? So if our entire data set, 33 was the only outlier, you represent it as a dot. Even if there was other values, right, you would still represent them as dots if they are considered outliers. Okay, but then you take your outlier out of the consideration here, and your whisker, right, your whisker now becomes your next highest point that isn't an outlier, right? So apparently in this data set, the next highest point besides 33 was all the way down here at 17. Okay, and so this is a really good example here of how one point drastically changed the shape or the look of our graph here, right? It made that whisker huge. Okay, but we can do this calculation for our outliers and figure out that it should not be included, and we can just represent it as a point there. All right, so then of course range quartiles and interquartile range is talking about the spread of the data. All right, and looking specifically at the 5-number summary, drawing our box plot with our new quartiles, and then understanding interquartile range and its effect on outliers. Okay, of course, obviously do this one. Again, the trick being making sure those numbers are in order before you start. Okay, and then finally here, last little information is going to be talking about measuring the spread. Oh, I'm sorry, we just talked about measuring the spread there. All right, but we're gonna continue on with this guy here. All right, so and we're gonna talk about the standard deviation here. All right, so we're gonna talk about the standard deviation here. All right, because sometimes our mean or our average value just doesn't tell us enough, right? So if we look at these two data sets, all right, 99, 1,000, 101, the mean is 1,000. But also if I go 0, 1,000, 2,000, my mean is also 1,000 there. All right, so clearly it has the same center point, right? It has the same mean, but these two data, if we would plot them on a histogram, would look drastically different. Okay, they would look drastically different. All right, and so what we can talk about here is measuring the spread of the data, and actually calculating that out. All right, if we were to look at it graphically, okay, we have our data set here. We could plot it graphically. All right, our mean, right, our average value ends up being 10. Right, our average value ends up being 10. And what you can see here is the orange dots are the values in the data set, the blue dot is the mean, and the arrow shows the distance from each value to the mean, right? So very close, farther away, far, farthest, right? So it's showing you the distance between the center point and all the other points. All right, and what we can do then is do this thing called our deviation, right? And to look at this mathematically, what this is doing is we could figure out the distance between the center point and all those individual points. All right, we can find that difference, and we can take it and add all of those differences together, right? So how far is each of those points away from our mean value, right? And so what we can do here is write it as x1 minus x bar, right? And remember, x bar stands for our mean. So if we look here, all we're doing is that we have 2 minus 10, right? And then we're adding that to our 5 point minus 10. And again, let me show you what that looks like. So again, 10 being here. So that's 2 minus 10. So this range, this little tiny distance here is 8. And then maybe this one's 5, then 3, then 2. Right, and when we add them all together, it ends up being 0 here. All right, so that doesn't give us any information when we try to sum up the difference here. All right, but what we can do is we can use that same kind of logic here, but we can find the average, right? We can find the average of that, and we can then use that to find our actual values that make a difference here. All right. And another thing we have to notice is that obviously when we were doing our first original, right, we had negative values. We had negative values if the point was lower than the mean. So in order to accommodate for that, we can actually square it, right? We can square it because that accommodates for the fact that it might be positive or it might be negative, but regardless, when you square it, the answer is going to be out as a positive number there. All right. So what we can do again is take the difference like we did between the center point and the individual points, and then we can square them. All right. We can square them. And then once they're all squared and you add them together, right, you can divide by the total number of points that there were. And what this is going to do is this is going to give us a variable called variance. All right, our variance. And the formal definition of that is a measure of the spread between the data points and the mean. Right, so we're measuring how far each of the data points is from the mean. All right, and that's exactly what we did. We measured the distance between each point and the mean. We squared it, and we took it over the average number of points, or sorry, the total number of points. All right, and something I hope you can find maybe easy to help you remember that you need to square the top is the symbol here is s squared. Right, the symbol here is this s squared. So hopefully that's a little helpful hint that you have to square the difference between the values there. Okay, so then looking at this equation here, hopefully we can just read it out straight. But again, remember what it's saying is this little e, this sigma here, is our summation, and it's saying from values 1 to whatever you decide, right? So from values 1 to n, you're going to plug them in here, right? And what this is saying is you're going to take each point minus the average, and you're going to square that. And you're going to add on the next one. So again, here at this top, this was 0.1, this was 0.2, this was 0.3, right? But the values, right, are whatever the point was. So this was 2 minus the average of 10, and we're going to square that. And then this little sigma here means sum. So we're going to add the next one, and the next one, and the next one until we take up all of those points there. Okay, and then of course we have this coefficient out here of 1 over n minus 1. Okay, 1 over n minus 1. So we shift it slightly from looking at the average, it's to the average minus 1. Or sorry, the total number of points minus 1. So n minus 1. So if we have 7 points, we're going to do 7 minus 1, which gives us this 6 here. Right, 7 minus 1, which gives us 6. Because again, think about it, you're now taking all of the points in relation to your average point. So you don't want to include your average point, which is why we do n minus 1. All right, so again, steps, breaking it down step by step for finding the variance, okay? The first step is find the mean. Add them all together, divide by the total number. All right, then for the variance, you need to use this equation where, of course, you're going to subtract the average from each individual point. So 2 minus 865, and then part of this equation is to square it. All right, so then I add, and I look at my next value of 25, and my next value of 50, 305, 309, 800, 4004. All right, and I add them all together. And then I multiply by 1 over n minus 1. So now I'm not looking at the 6 points, I'm looking at 5 points. All right, and we can divide them, and what this is saying here is that we have a huge variation. We have a huge variation, and the reason being is because, look, we're covering values from 2 all the way to 4,000, right? And so this huge s squared value, or this huge variance here is saying that this data set is not very close together at all. That's all it's saying, is because the data is so spread out. all right? But if you have something here, right, where they're closer together, this value of 49 seems a lot more reasonable here, right? It's a lot more reasonable, okay? And in fact, since we know our variance, we can very easily calculate our standard deviation, because standard deviation, we just take the square root of our s squared. So our standard deviation is actually just the square root of our variance. So it's 7 in this example here, right? So again, the smaller the number, the closer the data is together here, right? For this one, variance of approximately this, all you have to do is take the square root of it, right? We're going to get rid of the square on top. Okay, and if we look about just a couple quick facts, because we're going to obviously cover this more here, all right, in general, data that has a large standard deviation is very spread out. Same thing with its variance. If it's a very large number, it's very spread out. Okay, closer together, it's going to have a small standard deviation, small variance, all right? A data set that has a standard deviation of 0 is where all the data values are the same. There's only one value, and it's, I don't know, 3, right? 3, 3, 3, 3, 3, 3, 3. There is going to be a 0 standard deviation. All right. Another thing, standard deviation can never be negative. All right. So we got rid of our negatives for our variance by squaring everything, right? And then I know we said to take the square root of our variance to get our standard deviation. And normally when we take our square roots, we have that plus and minus our answer. But for standard deviation, we're only going to focus on the positive value. All right, and then most of the data set lies within one standard deviation of the mean. All right, and what that means there is that it's not usually more than one standard deviation. So if we look here, our standard deviation for this really large one is about 1100. Okay, so if we look, each value is within one standard deviation of the mean. So if my mean is about maybe 1500, right? I'd have to find the actual average here, but if it's about 1500, everything is going to be about within this 11,000. So 15,000 plus 1,000 and plus, and minus 1100. Okay, so everything's pretty much within there. And again, this one here is very spread out because look at how large that standard deviation is. But something here, it's got a standard deviation of 2.5. So everything, if my average value is about 32, right, 32, everything's with usually in what we like to say plus or minus that value, plus or minus 2.5. So it's within usually 32 plus 2.5 and 32 minus 2.5. All right, and then this right here, obviously all these values are 0, so we have a 0 variance and a 0 standard deviation. Okay, so then standard deviation is a measure of the spread that relies on our mean. Right, it relies on that average value there. And knowing the formulas for variance is going to be important, and remembering that variance is s squared, standard deviation is just s, so you take the square root to get from variance to standard deviation. All right, making sure you appropriately can do the variance and do the distribution here. That's going to be really, really important for moving forward here. All right, looking at the check your understanding. All right, talking about obviously our central tendencies, mean, median, mode. All right, then figuring out how to actually solve for them. How do we solve for our mean, median, and our mode? Right, that's important. And then really understanding the different components. So what does it look like when we're measuring spread? How do we measure that? What's the 5-number summary? It gives us this thing called a box plot. So what does a box plot look like? What do the different parts mean? All right, and then is there a way to make this even more descriptive? Yes, look for your outliers. Right, look for your outliers. So then you can modify your box and whisker plot to tell you even more. All right, and then we looked at the spread of distance based on mean values. So again, looking at standard deviation and variance there to kind of close that one out. All right. Again, this checkup is going to be super important because I get it. That was a really long kind of lesson there. So please make sure you're doing some of these. Again, formulas are at your disposal. So as long as you can read them and you understand what it's asking you, you should be good to rock and roll here. Okay. So then, of course, it's just going to ask you mean, median, mode. And again, the trick for a lot of these here is making sure that they are in order. Making sure they are in order is going to be huge. All right, then in order to calculate these, of course, you're going to have to figure out the different points. And one of the major points there is the median. All right, our median and our mean are our major points for most of these. All right, and then finally, variance and standard deviation. Okay, so obviously, if we can calculate our variance, we just take the square root of our variance, and that will give us our standard deviation there. Okay, and again, we'll work more with standard deviation moving forward. All right, so there are 3 quizzes here. I know it's pretty lengthy, but again, I personally like it. It's a natural break in this study here, so you don't have to focus on too much. All right, so first one here is only on the measures of central tendency. The next one is specifically going to talk about quartiles and box plots. And then that third quiz is going to talk about the measure of spread. So that standard deviation, the variance, what does that all mean? Okay, and so that concludes our weekend lecture here. I get it, it was super long, but again, try to keep up so that way we can be done at the end of week 3 and only have to worry about our final exam here. Of course, if you've got questions, comments, concerns, watch this as many times as you want. Reach out to me through email. I'm always here for you guys. All right, other than that, have a great rest of your weekend, and I will see you on Zoom, normal class on Monday.